Okay. Hello, everyone. Thank you for coming today. My name is Anneka, and I will be talking about opportunities for PVT district heating. So I'm a PhD student at UCL, but this was based on my Master of Research study, which leads into my PhD. So as I mentioned, this is a case study, and it was based on London project. But the methods could be applied to other countries and regions in ways that I'll explain how that can be done. So just to give you a background, based on this UK study, the UK is very gas reliant. A lot of homes, you'll see a boiler in their home. And UK emissions produced by gas for space and water heating account for about 14% of the UK's total emissions. And 53% of this is from domestic heating. So I want to ask, how will the UK look in 2050? Well, actually, globally, it's predicted that 70% of the world's population is projected to live in urban areas by 2060. And with 67% of current energy-related emissions produced in urban areas such as cities, my project looked into a particular house type in England, the terraced house. So I chose this particular house because 68% of the London building accommodation types comprise of low-rise purpose-built flats, converted flats, or terraced houses, such as the one we can see here. Also, I chose this house because it is quite an old building, I think about 78% of them are built after 1919 and the rest are built before 1919. And 80% of the existing stock in England is predicted to still be here in 2050. So there's quite a need to look into how to integrate systems into these old types of houses. So I'm not sure if any of you have heard of Photovoltaic-Thermal before, PVT. This is basically a solar panel that produces electricity and heat in the same area, and it cools down the photovoltaic cell to increase the efficiency and remove the heat at the same time. It presents to be a promising alternative to clean heating solutions in densely populated areas, since it produces the heat and electricity in the same space as I mentioned. And this study identified several benefits of having a single PVT system with storage, so batteries and hot water tanks, spread across multiple buildings. And these benefits were an asynchronous demand. So there could be more diversity in the heating demand, with people working at different times and showering at different times of the day, and having different routines. And so typically wasted heat during low demand periods could instead be shared across the heat network instead of incurring storage losses. Also, you have the benefit of more space. Realistically, if you have a small flat, you won't want to really have batteries and hot water tanks installed in your home. So if you could have a communal storage space, there may be more opportunities. It could present to be a more attractive solution. Also, if you have part of the house that has a shaded roof, there could be more flexibility in the installation, since if one house you can't use their roof, perhaps you could use a little bit of their storage to compensate, or just use another part of the roof that is unshaded. So to model this system, I used Modelica Dymola, and I used the building Modelica library to build up a system. And you can see on the far left, on my left, the high-level system diagram for the PVT model with storage. So it has the solar panel at the top, the heating panel, and the PV cell We've got the hot water tank and an auxiliary heater, which basically tops up the tank to a set temperature. So if it's 60 degrees and the sun wasn't producing enough heat to keep it at 60 degrees, the auxiliary heater would turn on and heat it. And then I've got the terraced house, which was a demand profile created, drawing heat constantly from the tank. So Modelica was ideal for this. You've got on my right, the basic schematic of my diagram. So I modeled 5 different system configurations based on a base case with the basic parameters shown on the table on the right. And in these different configurations, I varied the auxiliary heater size, the auxiliary heater set point from 60 to 80 degrees, did an open loop preheating configuration. This is where, instead of being in a closed loop of the PVT with the hot water tank, the mains water was first passed through the PVT and then it was fed into the hot water tank to preheat it. And I used 16 meters squared as the standard roof area, since this is the standard roof area for a terraced home. And I used weather data, an Energy Plus IWEC weather file. So this is basically a file that is compiled from up to 18 years of weather data, and it's representative of typical weather. Now, there are some limitations on this because we don't know how the future weather is going to change, so that needs to be beared in mind when looking at the results as an uncertainty. And so I mentioned the terraced home was modelled with a hot water profile, and this was calculated using a BREEDM domestic energy model. This is a method to calculate energy and fuel requirements in dwellings. It's commonly used in the UK in the building sector. And this says hot water demand is equal to this equation where N is equal to the number of people in the home. And on the graph we can see here, this is based on an Energy Saving Trust study where they measured a lot of homes' hot water demand. And I recreated a file suitable for my study based on their data. And you can basically see there's peaks in the morning at 7 a.m., I think that is, and 7 p.m. So that's probably when people are having showers or cooking. And this is basically the same throughout the year. I created this to be the same because hot water demand doesn't vary too much throughout the year. And I also looked into space heating, in particular low temperature space heating. And I chose this since this type of system could be integrated into ground source heat pumps. And there has already been some work on solar with ground source heat pumps. So this could be some future work to look into because it's quite a promising area. Also, low temperature heating ensures a greater energy efficiency in homes since it needs to be renovated to be suitable for this type of system. And due to lack of data, just a theoretical design heat loss was used for a post-1919 uninsulated terraced home. And as I mentioned, about 78% of terraced houses are post-1919, so it's quite representative. So onto the results. As we can see here, below about 3,780 watts per meter squared per day solar irradiance, which is the x-axis. The auxiliary heater, which is the power on the y-axis. The auxiliary heater was pretty much constant for all the scenarios, apart from the preheating case. So in the other configurations, the thermal output was not being utilized in the direct loop since the tank was already at 60 or 80 degrees. And due to the controls, which I used and is typically used in installations, the hot water tank would not draw heat, turn on the solar pump to draw heat from the solar panel, so it couldn't provide any useful heat. So it was better to just use the auxiliary heater. So in this case, the preheating scenario, which goes diagonally up with the blue line, performed much better. And in this case, all the hot water demands were met. This was actually for a row of 10 houses, and about 91% of the electricity demands were met for the house on the PVT system with battery storage. So I just mentioned battery storage. I looked into how grid-dependent this system was without batteries, and it was very high. It was about 71 to 87%. So that is the grid supplying electricity to power the auxiliary heater and maintain the set point. So you can see here at the graph, the top one shows a high cloud cover day, with the blue bits showing when the auxiliary heater came on, and the red line, the PV output, so it's very little. And then we have on the sunny day with no cloud, just below, you can see the auxiliary heater comes on a lot less, and there's a high PV output. So basically, I'm sure you know England doesn't have the best weather, so there may be more days, such as the first one. And in fact, I looked into the weather file, and about 32% of the days actually required about 100 kilowatt hours per day of auxiliary heating, and that would have been from the grid. But I did find that with battery storage, you could significantly reduce the grid dependency. So yeah, I did a rough calculation with you could have 102 kilowatt hour nominal battery capacity at 80% depth of discharge. And with all the inverters and wiring, this could roughly fit into an 8-foot shipping container. So for 10 homes, you'd have that kind of storage size for them, the communal storage size. And onto the space heating. From January to March, about 7.5% of the space heating was covered by the PVT thermal output, and 33% with the electrical output, so 41% in total. But bear in mind, this was based on the uninsulated home, which realistically, you wouldn't install this type of system on such a poor, efficiently type of house. So although uninsulated terraced homes are very common in the UK, a recent report from the government stated that homes, as many homes as possible, need to be upgraded to Band C energy performance rating by 2035. So that's the rating chart on the left. So there could actually be a big opportunity here to upgrade homes to be suitable for low temperature heating whilst upgrading them to this Band C or higher in line with the government's plans. And onto the PVT efficiency. A standard PV module can actually reach 110 Celsius on a sunny day. And with storage, could reach 110 degrees on a sunny day. And this could result in a 43% efficiency drop, since electrical equipment, as it heats up, the efficiency reduces. So applying a 0.452% efficiency drop per Celsius derating factor, without active cooling, the annual PV output would have been reduced by about 15%. So in the open loop active cooling configuration, up to 15% more electricity could have been reduced compared to a standard PV with no cooling. Emission savings. So with a carbon intensity of 0.185 kilograms CO2 per kilowatt hours for gas and 0.270 for electricity, based on the best scenario, each house could have saved about 3.2 tons of CO2 per year if previously gas heated, or 2.3 if electrically heated. So in perspective, the UK average household emitted 8.1 tons of CO2 per year in 2014, so it's quite a significant potential saving here. So just to wrap that up, there is a case to implement battery storage with PVT systems due to the high grid dependency found in this study. The PVT electrical and thermal efficiency and output can be increased when the mains water is preheated in the PVT due to the active cooling before entering the hot water tank. And there is actually a potential for meeting a higher proportion of occupant energy demands with larger PVT systems and communal storage compared to single dwellings, looking at previous studies that have looked at single house dwellings and PV and storage. So future work I'm working on now, I'm developing a more detailed model for the house, as in this study it was quite a basic house profile. And I'll be using co-simulation methods, so I'm actually building up heat zoning in Energy Plus, and I'll be co-simulating this with Dymola Modelica with the PVT system. And yeah, just bearing in mind, although the findings are geographically sensitive in this study, the methods could actually be applied to other locations if you just change the heat demand profile and the weather file. Thank you very much for listening.